Welcome to this explainer. Look, today we are tackling one of the absolute most notoriously tricky areas of the Cambridge IGCSE physics syllabus, radioactive decay. But here's the thing, we aren't just going to look at the raw physics, we're going to look at exactly how you present that physics to the examiner. I want you to think of an Olympic gymnast for a second. A gymnast can have all the raw strength in the world, they can do all the flips and practice, but if their routine lacks precise execution, or if they stumble on the landing, the judges deduct points mercilessly. The exact same principle applies to your physics exams. Let's imagine two hypothetical students. We'll call them Alex and Sam. Alex overloads every answer with raw physics facts but offers zero actual analysis. Sam completely rushes, misses the command word requirements entirely, and just throws numbers on the page. Both know the science, but both lose the marks. Securing top marks requires the precision and step-by-step execution of a carefully choreographed routine. Today, we are going to completely master that routine, so every sentence you write is a graceful landing.
Okay, so let's dive right into this core tension. You've studied the textbook, right? You know what an alpha particle is? You completely understand half-life. Yet, when the test results come back, the marks just aren't there. Why on earth do students who completely understand the science still stumble? Well, the source material we're analyzing today reveals a pretty fascinating truth. It usually isn't a lack of knowledge at all. It's a failure in evaluating evidence and drawing conclusions in the exact, highly specific way the Cambridge examiner expects. It's all about how you process the data sitting there on the page and translate it into a structured, undeniable answer. If you're like Alex and you just word vomit facts, or you're like Sam and you ignore the command words like evaluate or deduce, you're leaving easy marks on the table. It's about cracking the code of the assessment objectives.
To fix this, we've broken this explainer into three crucial parts. Part 1, core principles of decay. Part 2, the method mark routine. And Part 3, the examiner's deductions. Starting with Section 1, core principles of decay, the raw elements of physics. All right, let's look at the baseline. Here is the precise, non-negotiable definition we are working with, straight from the syllabus. Radioactive decay is a spontaneous and random change in an unstable nucleus, resulting in the emission of alpha or beta particles and sometimes gamma radiation. Now, before we break down why every single word in this definition matters to the examiner, I need you to do something. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the physics. You are dealing with an unstable nucleus. The change is spontaneous, meaning it happens completely without any external trigger. You can't heat it up, cool it down, or put it under pressure to make it decay faster. And the result is the emission of specific particles or high-energy radiation. This is your absolute foundation. If you don't have this locked in, the analytical gymnastics we're about to do won't work.
And this right here brilliantly illustrates a vital distinction that catches students out every single year. We're talking about cause and effect. The timing of the decay is a completely random process. You literally cannot predict exactly when a specific individual nucleus will decay. It's much like rolling a massive set of dice. However, and this is a huge however, the result of that decay, the transmutation into a completely different element during alpha or beta emission, is a highly specific physical certainty. The timing is completely unpredictable, but the physical consequence, absolute guarantee. An alpha decay will always reduce the atomic number by 2. Period. Understanding this duality, the random cause versus the predictable physical effect, is the absolute key to unlocking those higher-level analytical evaluation questions that separate the top grades from the rest.
Let's move into Section 2, the method mark routine, where we execute the standardized sequence. This is where examiners award marks for your systematic processing, not just the final magical number you write on the answer line. Just knowing the physics isn't enough. Top-scoring candidates follow this exact 5-step standardized sequence to extract data and draw evidence-based conclusions. You can think of it like the Peel framework, point, evidence, explanation, link, but adapted specifically for physics math. First, you identify the key elements in the question. Are we dealing with alpha or beta? What's the starting isotope? Second, apply the relevant principles, like the conservation of mass and atomic numbers. Third, execute your analysis with totally clear step-by-step working. Do not skip lines. Fourth, verify your results. Take a second to look at the new atomic number. Does it actually make sense? And finally, fifth, present your answer in the appropriate format. If you skip these steps, if you rush like our hypothetical student Sam and just guess the final element in your head, you will lose those crucial method marks. even if your final answer is right. The examiner needs to see the routine. The process is the product. When you are actually executing the problem-solving phase in the exam hall, you need to rely on this specific framework to prove your analytical depth to the examiner. Imagine you're looking at a massive, complex half-life data chart. Step 1 is to deconstruct. Scan that data and extract only the relevant given information. Step 2 is solve. Break the problem into logical, bite-sized mathematical steps. And step 3, evaluate. Listen, this is the absolute hallmark of a top-tier student. Check your answer for reasonableness. If a question gives you a command word like evaluate, you must identify limitations in the data, you must question the assumptions made in the experiment, and you must justify your final decisions using the exact numbers provided. You aren't just a calculator, you are an analyst evaluating the physics in front of you. To help execute this flawless routine under the immense pressure of the exam hall, the source material highly recommends a memory hack. Try creating your own mnemonic out of the first letters of these steps, or the key terms of radioactive decay. When the clock is ticking down and your heart is beating fast, a simple mental trigger can snap your brain right back into that standardized sequence. It stops you from panicking and reverting to disorganized, messy calculations. But hey, before we move to the final section, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGC to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGSE and turn on all notifications so you never missed our weekly exam strategy sessions.
All right, Section 3, the examiner's deductions. Let's look at the critical warnings and evaluation pitfalls.
Here, we are looking at the exact opposite of securing marks. We are looking at a literal cheat sheet of what annoys the people marking your paper, drawn straight from the principal examiner reports. Examiners repeatedly flag these 3 highly avoidable mistakes. First, candidates frequently lose points by confusing cause and effect. They mix up the random, spontaneous timing of the decay with the very real physical transmutation effect we talked about earlier. Second, students completely ignore format and presentation. They lose absolutely easy marks for sloppy notation, missing units, or unreadable graphs. And third, the biggest, most devastating trap of all, providing a beautifully written, entirely generic answer that completely ignores the actual context of the question.
This crucial point is perfectly captured in this comparison. Imagine a find the flaw exercise. A student like Alex might write down a perfect, textbook-accurate definition of beta decay for a 4-mark question and still score an absolute 0. Why? Because if the question is about using a specific beta-emitting medical tracer in a hospital, and the student didn't mention the hospital, the tracer, or the specific half-life data once, the answer totally fails the command word requirement. Never, ever provide a generic answer. Conversely, a top-scoring contextual answer links every single point to the given scenario. They question the assumptions of the specific experiment shown. They use the numbers provided in the specific data table. You have to anchor your physics knowledge directly to the reality of the question prompt.
Landing the perfect score means building a system and adhering to these strict conventions. As this quote highlights, proper headings, correct terminology, appropriate formats, and clear annotation are not optional extras. They are the actual language of physics. If an element transmutates, you must use the correct atomic notation. You must label your axes on a decay graph with units. You need to manage your time matrix so you actually have the seconds left to double-check these annotations. If you want the examiner to treat you like a top-tier physicist, you have to present your work like one. It's that simple.
As we wrap up this explainer, I want to leave you with this final thought. Your raw physics knowledge might be incredible. You might know the Cambridge syllabus inside and out. But as you sit down for your next past paper, ask yourself, is your analytical routine disciplined enough to secure every single available method mark? Are you merely memorizing facts, or are you truly ready to execute the examiner's strict routine flawlessly, just like a gymnast sticking that perfect landing? Focus on the process, decode those command words, link your knowledge to the context, and those top marks will absolutely follow. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder: subscribe to our YouTube channel Ace the Exams, at @acetheexams_IGCSE, to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.